other exercises that we have considered yesterday are two exercises that I suggested you to solve using Markov chains. Now, we have introduced Markov chains as a special type of process, of stochastic process, which is, I repeat, just a collection of random variables indexed by some index space. That can be time, that can be space, or whatever you want. But we have this collection of random variables that represents nothing more than the random evolution of a phenomenon over time, over space, over time and space, whatever you want. For example, if I look at the price of an asset, this is something that has an inherent variability that is random for me ex ante, so ex post. I know that yesterday the price of one share of Google was that, but today I don't know what will be the price next week. I can try to guess that, I can try to make predictions, so we use stochastic processes. A Markov chain is a very important type of stochastic process in which we have the Markov property. Now, the Markov property tells me that the probability that tomorrow I will be in a given state, or the probability that at time step n+1 I'm in a given state, just depends on where I am today, or where I am at time n. Okay, so the probability that at time n+1 I will be in state j just depends on the fact that today I'm in state I. And using this transition probability, I can build the transition matrix and I can build the transition graph that I've seen is a graphical representation of my matrix. Now, the two exercises that you were supposed to consider are the following. In the first one, we have two players, A and B. A has €1 and B has €2, and they are playing a game. And this game is made of different rounds. We don't know which game, but it's not important. What we know is that at every round, the winner gets €1 from the loser. And we also know that, given the historical information, A is a better player than B, or is just luckier than B. And the probability of winning a single round is equal to 2/3, okay? They start playing the game, and the stopping rule, so the game stops when one of the two players goes bankrupt. That is to say, his wealth or her wealth is equal to 0. So, for example, if you consider player A starts from 1. If player A wins, he or she goes to 2, but if he or she loses, it goes to 0, and the game would stop. The question is, what is the probability, if they start playing this game, that A actually wins the game? And my suggestion was, there are different ways in which you can solve this exercise, but was to try to think about Markov chains. There are two types of equations that I want to discuss with you. The first one are the absorbing equations. Now, these equations are useful to understand what is the probability to reach a given absorbing state. You remember what is an absorbing state for us? Yesterday, when we were showing the example of a Markov chain, we saw that in that example with 4 different states, state 4 was absorbing. What does it mean? Once you reach state 4, you stay there, so you cannot escape. For example, in credit ratings, if you are considering a counterparty and that counterparty goes default, it is over. So you cannot come back from default. You can move from a AAA class to a BB class. You can improve from a BBB class to a AA class. You can go from B to C, from C to A, whatever you want, with different probabilities, obviously. You can stay in your class, but once you go default, you are done. That's it. So what we want to do using the absorbing equations is to determine what is the probability to reach a given absorbing state I, And we can use that, you can do that in the following way. So we look for the solutions that are unique, A1 up to AM, such that AI is equal to 1. Remember that I is our absorbing state. So we want to check what is the probability of reaching that absorbing state. So we have that AI is equal to 1. For what concerns the other A's, from 1 to M apart from I, we set that AJ is equal to 0 for all the other absorbing states that are not AI. Okay, so if I have two absorbing states and I'm interested in the probability of reaching the first one, I will set the A of the other one equal to 0. Okay, and I will just set equal to 1 that of the absorbing state I'm interested in. So AI is equal to 1, AJ is equal to 0 for all the other absorbing states that are not I, and for all the other states that are not absorbing, so they are transient, and this is my computer that does not know mathematical English and then corrects me. The transient states, I compute AJ equal to the sum for K from 1 to M, so all the states, of AK PJK. So what we will get is essentially a series of equations. I will have an equation for each one of the A's I have to solve. So this is a system that I can identify, I can get the solutions. And with an example, it will be extremely clear what we have to do. Once I have the A's, I immediately have the solution for my exercise, because I can tell you what is the probability of reaching an absorbing state. And in exercise number 7, essentially, winning is an absorbing state. That is to say, you have all the wealth, the other guy has nothing, so he has to stop. Okay, now you should see my my iPad where I can write, and we will try to solve the problem together. Now we start from the exercise of the two players. Okay, so we have the two players A and B. Player A starts from €1 and player B starts from €2. And what we know is that they will stop when one of the two reaches a wealth equal to 0. Okay, so at any time step, what we immediately have is that the total wealth of this game is equal to 3. So the total wealth of this game is always 3. It can be that A has 1 and B has 2. It can be that A has 2 and B has 1. It can be that A has 3 and B has 3. Okay, and the other one necessarily has 0. So if we want, the state space for us is just given by 4 possible couples or combinations of the money of the two players. So the first case is A has 0 and B has 3. And that would be that the game stops because A has wealth equal to 0. Then we have the situation from which we actually start, which is 1, 2. Then we have the situation in which A goes to 2 and B goes to 1. And then we have the final situation in which A has 3 and B has 0. Okay, so these are the possible states. Now, what we are interested in is essentially the probability for A to win. Okay, so if we just consider A, the state space for A is given by these numbers. So if we want, I is equal to 0, 1, 2, 3 for what concerns our player A. Now, my suggestion is try to draw a Markov chain out of this example, exploiting what you know about the game. Now, the states for us are 0, 1, 2, and 3. These are the possible states of the game. Now, if I am player A, okay, so if I'm player A and I'm in state 0, what does it mean? It means that I lost all my wealth and B has 3. So if I reach state 0, it means that the game ends because one of the two players has gone bankrupt, and in this particular case, it's me, player A, that has defaulted. Okay, so what we have is that if I am in 0, I always stay in 0. I cannot escape 0. And this happens but with probability 1. So 0 is an absorbing state. So once you reach 0, if A has a wealth equal to 0, the game stops. So we cannot escape. So it's not possible to go back to 1, 2, or 3. The same thing happens if A reaches 3. Why? Because if A reaches 3, it means that A has a wealth of 3 euros that corresponds to B having a wealth of 0. Okay, so also for 3, if I stay here, I will not escape, and that happens with probability 1. Now, let's consider the other situation. Imagine that I'm in state 1, okay? So I'm in state 1, which is actually the starting point of my game, because A starts from 1. If I'm in 1, I have a given chance of winning the round and a given chance of losing the round, okay? Now, what I know is that my A has a higher chance of winning with respect to B, okay? In particular, what I know is that the probability for A to win the game, the round, sorry, is 2/3. So it's 2/3. And it's 1/3 the probability of losing. So if I'm in 1, I can draw a arrow like this that brings to 2. And the probability here is 2/3 because I can win the game and I go to 2. But I can also lose the game and go into 0. So this has probability 1/3. If I'm in 2, what happens? If I'm in 2, I have a probability, since I'm A, of winning the round, and that has a probability of 2/3. But if I'm in 2, I can also lose that round, and I can lose the round with probability 1/3. Okay, so what happens if I'm in 1, I can jump to 2, but I can also jump to 0. And since the A has a higher chance of winning, I can jump to 2 with probability 2/3, and I can jump to 0 with probability 1/3. And the same if I'm in 2. Then the interesting thing is that when I'm in 1, when I'm in 0 or 3, I cannot escape because this is the end of the game. The end of the game is given by two situations. Either I, that I'm player A, have no wealth left, or I have all the wealth, so B has no wealth left. Notice what happens if, for example, I want to draw the same stuff for B. If I want to draw the same game for B, the states are the same. It's 0, 1, 2, and 3. These are the same. Allow me to do this. So let's do that in another color. So we choose red for B. So for B, the 0, 1, 2, 3. Also for B, I have that 0 is an absorbing state. So if B loses, the game is over. If B wins everything, the game is over. So it's an absorbing state. Then if B starts from 2, okay, what happens? B has a chance of 1/3 of winning the game, but he also has a chance of 2/3 of losing the game. Okay, and then if I'm in 1, I have a chance of 1/3 of winning the game, and I have a chance of 2/3 of losing the game. So you see that the chain for what concerns B is different. Okay, so they are consistent and they are obviously related, But you see that the arrows have different masses, different probabilities, because we are assuming that the chance for A to win is larger. If you assume that the chance is the same for both, then you will essentially get the same chain for both players. But in this case, I'm assuming that A and B have different chances of winning a specific round, okay? Now, what we want to find is the probability that A wins the game, okay? So I want to find the probability that A wins the game. What is that probability for me? That probability for me is essentially the probability, if I'm A, that I reach one of the two absorbing states. State number 3. So I want to reach this. This is the state I want to reach. Because also 0 for me is an absorbing state. But 0 means that I've lost the game. I want to win the game. So for winning the game, I have to reach 3. Okay, we can then use the absorbing equations that we have seen before. Okay, so how can we do that? I have to find the unique set of equations, and in this equation I have to set the A of the state I'm interested in equal to 1, the A's of all the other absorbing states equal to 0. In this specific situation, there is only one other absorbing state, which is 0. And I set this A equal to 0. After that, I have to find A1 and A2 to complete the A's of all the states, because I have state 0, 1, 2, 3. Okay, so for 0 and 3, I already have the values of A3 and A0. I have to find the value of A1 and A2. Now, what is the for A1? For A1, that will be the sum for K from 0 to 3, okay, of P1K, AK. And for 2, it will be the sum for K from 0 to 3 of P2K, AK. Now, what is this? I just have to look at my chain. Remember that I'm looking at the chain of A. So this is the chain that I want to consider. Now, what is the probability that I can jump from 1 to 0? Okay, so what is the probability that I can jump from 1 to 0? It is 1/3 multiplying what? AK, that is to say A0, okay? Plus the probability that from 1 I jump to 2. So it's 2/3 A2. Then can I jump from 1 to 3 directly? No, I cannot. So in principle, if you want, you can also write that explicitly, but it will be 0 multiplying A3. Okay? Because the probability of jumping from 1 to 3 in just one step is 0. I cannot. They are not immediately connected in my chain. Now, if I do this, what do I have? I have 1/3 that multiply A0, but I know from this that A0 is equal to 0, plus 2/3 A2 plus 0. That multiplies obviously 1. So what I have is that this guy here disappears and this guy here disappears. What remains is 2/3 A2. What happens for A2 conversely? So for A2 that I have here, I have to do the same game. So What is the probability that from 2 I jump directly to 0? It is 0. So I can write 0, A, 0, which is 0 in any case. Plus, what is the probability that from 2 I go to 1? It is 1 over 3, A1. Plus, the probability that from 2 I jump to 3, okay? Because you see that, for example, the probability that from 2 I stay in 2, it is 0. So what I have to consider is just all the paths that are possible. So what I have is that 1 over 3a1 plus 2 over 3a2. Okay, so this is my a3, sorry, not a2, a3. Okay, because I have a probability of 2 over 3 to jump to state 3. Now, if I do that, this is obviously 0, and I have 1 over 3a1 plus 2 over 3 multiplying a3, but a3, I know that this is equal to 1, okay? Please let me just write that. Okay, this is 1, 3, okay. I once had, believe it or not, once I had a very nice handwriting. Now it's terrible because I had a motorbike accident, and after that I really lost my nice handwriting. Okay, but I hope you understand. Okay, so this is my second equation. Now, what do I have? I have to solve for a2 or a1. You choose. Okay, so since I know that a1 is equal to 2 over 3 a2, I can substitute in the second equation like this. So I have that a2 is equal to 1 over 3 that multiplies 2 over 3 a2 plus 2 over 3. Okay, if I solve for that, what does it mean? It means that if I compute a2 is equal to, this is 2 over 9, a2 goes on the other side, that becomes 7 over 9, a2. I simplify, and at the end of the day, I have 6 over 7. For what concerns a1, then I take a1 equal to 2 over 3 multiplying 6 over 7. Okay, this is 2 and this is 4 over 7. Okay, now what is the meaning of these A's that we have computed? These are the probabilities we are interested in. A0, the probability that I reach state 3 when I start from 0. What is that probability? 0. Why? Because I'm already in an absorbing state. So if I'm in 0, the game is over, I cannot go to 3. A1 is the probability that if I start from €1 as player A, I can reach, it's the probability of reaching state 3, starting from 1. A2 is the probability of reaching state 3 starting from 2, and A3 is the probability of reaching state 3 if I'm already in 3. Now, the probability of reaching 3 when I'm already in 3, it's 1, and that's why we set this one like this, and that's why we set for all the other absorbing state the probability equal to 0, because we know by definition that if I'm in an absorbing state, I cannot exit. Okay, so I only set equal to 1 for the absorbing state I'm interested in. For all the others, the probability is necessarily 0. So the probability of moving from those states to the state I'm interested in, if they are absorbing, is 0. So what remains for me are A2 and A1. But A1 is exactly the quantity I'm interested in, because I know that if I'm player A, I'm starting from an initial wealth of 1, and I want to know what is the probability that from this state I reach this state by playing several times and having every time the chance of increasing or decreasing my wealth. If I do that with my equations, I get A1, which is exactly my probability. That is the probability that I will win the game starting from an initial wealth of 1. Now, notice, this is very important. Please notice, don't make this error, because sometimes some students make this error. Okay, so A2 is not the probability that B wins. Okay, because, and you can see that immediately, because if I take this and you sum them, they don't sum to 1. So 6/7 and 4/7, they don't sum to 1. Because A2 is not the probability that B wins. A2 is the probability that A would win the game if the starting wealth of A were 2 instead of 1. And you see the chances are larger. Makes sense. You are closer to winning. And so for A, the chances are larger. If you want to compute the probability for B to win when B starts from a wealth of 2, so if you want to solve the mirroring problem, then what you have to do is to, in a sense, if you know what is the probability for A to win, you already know what is the probability for B to win. But if you want to solve this exercise using the chains, you have to perform the same computations that I made here for you, but you have to use the probabilities of B. What you will have that A3 is also equal to 1. A0 is equal to 0. This is always the case. But for A1, for example, instead, the probability of jumping to 0 is when you are 2 is no longer this, but it's 2/3. This probability is 1/3, and so on. Okay, this is how you solve this exercise using chains. So I repeat, we start from a game with 2 players, okay, A and B. A has an initial wealth of 1, B has an initial wealth of 2. And then they enter in this game. A has a higher chance of winning each round, which is 2/3. Now, the states of this game are just 4, okay? So I can be in the situation in which A loses and B wins, which is 0/3. I can be in the opposite situation, so A wins and B loses 3/0. And then I can be in the intermediate situations, 1-2 to 1. If I'm interested in A, the clever thing to do is to write the Markov chain in graphical form. If you want, you can also use the matrix. Okay, so if you want, you can write 1, 2, 3, and so like this. And then you can see that the probability that if you are in 0, you stay in 0 is equal to 1. The probability that if you are in 0, you go to 1 is 0, 0, 0. And this will be 1, 0, 0, 0. And then you have the probability that if you are in 1, you go to 0, it's 1/3. The probability that if you are in 1, you stay in 1 is 0. The probability that you are in 1 and you go to 2, it's 2/3. And this is 0, and so on. So you can complete. So the probability that you are in 2 and you stay in 2 is equal to 0. This is 2/3. This is 1/3, and this is 0. So if you want, you can also use these. What is more convenient for you, okay? What is important is that you remember how to use these equations. These equations can be boring, can be long, but I hope you will agree with me, they are not difficult. You just have to solve the system in which the probabilities are given, because they are essentially given by the problem once you have written the transition matrix or the chain. And after that, you solve for the different case. And you will always have some values of A that are already fixed. So the absorbing state that you are considering is always 1. And for the other ones, they are all 0. So that reduces, if you want, the complexity of the system, because a lot of things disappear and other things are just constant. And then you solve and you get. A1 would be the probability that you reach the end of the game winning if you start with €1. A2 is the probability that you win if you start from €2 if you are player A. I repeat, for player B, you have to solve a similar system, but with the probabilities of B. The only situation in which you will not need to do that is when the probability of winning is the same for both players, okay? But this is not a symmetric game.